very important. As you know, an isomer is a compound having the same molecular formula but different structural formulas. And examples are given to you here. I've got propanoic acid and methyl ethanoate. Of course, we know this is a carboxylic acid and this is an ester, and they are always, carboxylic acids are only ever the isomers of esters, and you should know that. And of course, you can look at other different types of isomers as well. And what I have here specifically, you need to know 3 different structural isomers, namely chain, positional, and functional isomers. Please go through that again. Isomers mainly have 2 main groups, which are stereoisomers, which are spatially, it looks exactly the same with the same substitute, same elements, and the same, you could say it's exactly the same structure, but you get optical versus geometric isomers. Optical isomers are just mirror images of each other. As you can see, same elements face each other. And then geometric isomers, of course, have substituted groups just on different sides and different levels of that specific compound. So you can have cis and trans organic geometric isomers. We are focusing on the structural or constitutional isomers, and you can get chain positional and functional isomers. Of course, you need to know what the difference between those are. And if you look at propanol versus methyl ethyl ether given to you here, what type of structural isomer would they be of each other? Of course, would it be chain? Would it be positional? Would it be functional? Of course, it would be functional, because you have completely different functional groups in these organic substances. We have learned about 3 different structural isomers, namely chain, positional, and functional isomers, and you can identify these types of isomers below. I would like you just to pause the video, look at the isomers, and then make your choice and think of the reason why. So for the first, we have pentane, and we've got 2-methyl butane. They've got the same number of carbons, the same number of hydrogens. They've got the same molecular formula, but different structures, different arrangements of the carbons and hydrogens on the chain. This is a straight chain, and as you can see, this is a branched chain. So would you say this is a chain, positional, or functional isomer? Of course, it would. These are chain isomers of each other, because the only thing that is different is the way that the chain is arranged in each case. Here it's branched, and here it is a straight chain. What type of isomers do we have in this pair here? We've got 1-chloropentane and 2-chloropentane. So the only thing that has moved is and changed was the position of the chlorine substituent. So, of course, the only thing that has changed was the position. So these are positional isomers. Can you think of a functional isomer or functional isomers of each other? Here we go. We've got butanoic acid and methyl propanoate. They both have 1, 2, 3, 4 carbons in this case as well. 1, 2, 3, 4 carbons. They each have 2 oxygens, and they each have that extra hydrogen there, right? They have, here you have 3 hydrogens, Here you've got 2 hydrogens, these 2 hydrogens, and of course, you've got this hydrogen here. You're going to get exactly the same on this molecule. So you've got basically over here, you've got, 2 hydrogens here, 2 hydrogens here, 3 and 1. Okay, so that gives you 8, and here you've got 6 and 2, so that's also 8 hydrogens. So these, of course, are functional isomers of each other, because the functional group differs, right, in each case. They are still isomers of each other. They've got the same number of carbons, same number of oxygens, and same number of hydrogens, but the way that they are arranged give completely different functional groups. And these are always functional isomers of each other. You have this as your carboxylic acid, and a functional isomer of any carboxylic acid is always its equivalent ester. Please make a note of that. An ester would always be a functional isomer of an equivalent carboxylic acid, meaning they have the same number of carbons, hydrogens, and oxygens.